code. Okay, I just hit play, and then it asks me how many players, 1 or 2. So I'll start off with 1. Okay, and it says should the computer play first or second, and I'll say play second. Okay, and so it's asking me where I want to play, so I will play in the center, and then the computer has chosen up there, so I'll go spot 1. Okay, and then so now the computer has blocked my win here. So now I'll try to figure out. Oh, so now I got the computer trapped, right? Okay, 7. Oh, you can't can't do anything now, right? So the computer had to choose, right? And then so now I can win with a 4. And it says X wins, and I go yes. Okay. So you know, the computer is not optimized or anything here, because perfect gameplay would always result in a draw. Here we'll maybe I'll have the oh, maybe I'll go again. Let's see. Computer goes there. I'll go here. Now, if I try to play in spot 3, it'll tell me enter valid move. So I'll go 4. Oh, and then the computer wins there. Okay. So anyway, that's that. I don't know. Are there any questions about this?
How much error handling do you want? Like, do you enter characters, they enter integer values, they enter...
I don't know. Of course. All right. Let's see what happens. I don't know if. Yeah. Okay. So it says I didn't program program that error handling here. Okay. So we'll say. But let's see if I put in an E. Okay. Yeah. It doesn't like that. So. Okay. Yeah. All right. So. Okay. Oh, something happened. NA is introduced by coercion. Okay, something. Warning message. Okay, I'm not sure what happened here. It said O wins, but then I'm also getting warnings. All right. O plays 9. All right, I'm not sure what happened there, but okay. But this is that's my my code here, and that's all it does. Okay. Well, let me close this out and load up today's lecture. Week 2, Friday. And we'll clear all of this out. All right, let's we'll knit this and open it up. Okay, so we'll talk about environments and debugging here. Okay, so environment. The environment is the data structure that powers scoping. Okay, it's kind of like a list, but it's different. Okay, in that it's an environment. Okay, and so the job of an environment is to bind names to values. Okay, so you can think of, you know, here's an environment and we've got 4 names in it, A, B, C, and D, and if you bind it to values, okay, this is essentially what's happening. Okay, so here I'm creating a new environment, and I'm saying A inside environment E is going to be false, B inside environment E is A, and so on and so forth. And we're just binding the names to particular values. Okay. In the Advanced R textbook, I'm just taking these diagrams straight out of Hadley Wickham's Advanced R chapter on environments, which gets really in depth. Okay, I'm kind of giving you like the short abbreviated version here. Okay, just kind of covering what I think are the key points as far as what you'll encounter. Okay. Every environment has a parent, which is another environment. Okay. And in diagrams, we're going to indicate that this thing has a parent by having a pointer over to here. This is the parent environment. And then this thing has a parent that, is pointing to somewhere else. Okay. And every environment has a parent. Okay. The global environment has a parent. Everything has a parent except for the empty environment. The empty environment is the parent of all environments, and it itself has no parent. Okay, but everything else has a parent environment. Okay, and so if it doesn't find, if you look for D in this environment, it's going to say, oh, I find A, B, C, but I don't see D, and then it'll go to the next environment, and it keeps going, climbing the hierarchy until it finds the thing that it's looking for. Okay, and that's called lexical scoping. All right, so the important environments that you should probably know are the global environment. This is when you start R and you start saving variables and things like that, they're saved in the global environment. Okay, this is the one where you're working and all of that. The parent of the global environment is the last package that you attach. Okay, and so if you don't attach anything, it's going to be like base stats or something. I don't know, something like that. All right, but if you attach some kind of package, that will be the parent of the global environment. It's the last package you attach. All right, the base environment is the environment of the base package. Okay, so it's like the last one right before the empty environment. Okay, so the base environment has one parent, and that's the empty environment. And the empty environment is the ancestor of all environments, and it's the only one without a parent. Okay, and then if you call environment, that's the current environment that you're in. Okay, most likely that'll be the global environment. If you type in environment right now on your computer, or in R right now, it'll probably say global environment. But if you're in the middle of a function or something, then you'll be inside there. Okay, so if you type in the command search, this will list all the parents of the global environment. Okay, and so this is the search path, because when you're looking for something, like in your global environment, you don't have a function called standard deviation, right? That's not programmed in your global environment. But obviously, when you type in SD, it finds a function that calculates the standard deviation. Okay, and so what it's doing is it starts its search in the global environment, says, oh, I don't see anything there. Now I'm going to move up to this parent package stats, and that's where it's going to find the standard deviation function. And it keeps climbing the thing until it finds whatever it's looking for, until it reaches the base environment, and then the only parent of the base would be the empty environment. Okay. All right, and so this is how our search path looks like. You start in the global environment. It points to, this is like package stats. Okay, package stats, package graphics, everything. Okay, until it gets to the base environment, whose parent is the empty environment. And the empty environment has no parent. There's no black dot here. Okay. And every time you load a package with library, it goes in right here. Okay, so you load a package with library, it goes in between global environment and this one. All right, and that's where it slides in. Okay. Most other environments, you can create environment using the command new environment, but I'd say most of the time the environments that are created are because you've run a function. Okay, and so when you run a function, or there's going to be 4 environments associated with it. There's the enclosing environment, the binding environment, the execution environment, and the calling environment. All right. Probably the one that you're going to have to become most familiar with will be the execution environment and the enclosing one. But these other ones are also there, and I guess when you get into the nitty-gritty, they can make a difference. All right. So the enclosing environment is the environment where the function is created. Okay, so wherever you write it and you're storing it, that's going to be the enclosing environment. Okay, and every function has one and only one enclosing environment. And then for the other types of environment, whether it be the binding, execution, or calling environment, there might be one or more, or even those things might not be associated with it. Okay. When you bind a function to a name, and this sounds strange, that you have this function that exists, but then when you bind it to a name, and you say like, I want to call this function, that creates the binding environment, right? And then calling a function creates an ephemeral execution environment. Okay, so you get this execution environment where the stuff that's going, the code inside, that's running inside the environment, that's where all of that stuff exists. That exists inside the execution environment. And then lastly, if the place where the function has been called, that's the calling environment. All right, let's talk about these. All right, so the enclosing and binding environment. So when a function is created, it gains a reference to the environment where it was made, and that's the enclosing environment, and that's where it goes for lexical scoping. So if it can't find, like if inside the function you're asking for some value and it can't find that thing, or if you're asking for another function and it can't find that, it's going to go to the enclosing environment where it was created, and it will start there the search path. Okay. When you name a function, all right, the environment where the name exists is the binding environment. Okay, so if you say like, I wrote this function and I'm going to name it function f, the f is used to the f is binded or bound to that function. Okay, and so where f exists, that's the binding environment. Okay, so in most scenarios, your enclosing environment and the binding environment are going to be the same spot. Okay, the enclosing environment and the binding environment, those will generally be the same environment in most places. Okay, the time and so here's an example. All right, we're storing the value y is 1. Okay, and I'm creating a function of x, and that function calls x plus y. All right, and we're going to call that f. All right, and this little arrow binds the function to f. Okay, and so if we ask where is the environment of f, okay, that's the global environment, and so so the binding environment is f. Okay, and then this and environment f, this is asking what's the enclosing environment, and the enclosing environment of this function is the global environment itself. So you can see the function has a parent or a enclosing environment. That's the global environment. The fact that f, the thing that we've named f, calls this function or is bounded to the function, this is also the binding environment. Okay, and then so when you run this thing, it's going to go to the parent thing because it's looking for y, and it's going to find this y is associated to the value 1. Okay, so function f is created in the global environment, so that's the enclosing environment. The name f exists in global environment, so that's the binding environment. Okay. The distinction between enclosing and binding environments is important for package namespaces. So as you know, when you start up R, it loads all of these packages kind of like without telling you, but right, like if you ask for search right now, it'll say like, oh, we have all of these other environments, right? It's got tools RStudio and package stats and all of that. So so package namespaces keep packages independent. Okay, so if you've got some package that uses the mean function in kind of like the base statistics, okay, and then over here you create another package that creates its own separate mean function, right? You can create another function called mean that does its own separate thing apart from the regular thing, right? The namespace, the fact that you've got this kind of enclosing environment separate from the binding environment is that it ensures that package A continues to use the base mean function and not the mean function that's written in package B. Okay, this is all detailed, explained a lot more detail in Hadley's book. Okay, I'm gonna say 99% of the time you don't have to worry about how this works, and it just does. Okay, like, you know, when you start creating your own separate standard deviation function, for whatever reason you want to do that, I don't know why you would, but if you did, you don't have to worry about these other things that might be using standard deviation to start suddenly using your own custom version of it. Okay, so and it's only when you start like, if you're creating other functions, you might want to specify, I want you to use my specific fancy standard deviation thing. Okay, if you're going to do stuff like that, it's probably better not to use the same name as a function that already exists, right? But then, you know, if you load like dplyr or something, it'll say like, the name in this thing is masking someone else, the function of another thing, right? So like filter, there's a function in dplyr called filter, and there's another function in kind of like base stats or somewhere else called filter, and they're different. And so you know, if you're gonna make a dplyr type package and you want to do something like that, then you have to worry about this. 99% of the time you don't. Yeah.
Does this happen when you make a function in the global environment? Does it affect, like, if you make the, like, let's say you make the mean function in global environment, you don't have a package,
right?
And then does it affect the package?
No, it does not. Okay, because there might be some other thing in I don't know, something else. Okay, and basically there's going to be a namespace created that is like, it's an environment called the namespace, and the things that will be the enclosing environment, but it's separate from the binding environment, so that when things call the mean function, it's finding it in the using the binding environment. So okay, so anyway, I guess don't worry about it, but it is there. All right, as the execution environments, and this is probably the one that you'll as far as environments go, this is the one that you're gonna have to think about the most. Okay, every time a function is called, a new environment is created to host the execution. Okay, the parent of the execution environment is the enclosing environment of the function. So wherever that function resides, as or is created, that is the enclosing environment. Again, if you're writing functions in the global environment, the global environment will be the enclosing environment. Okay, so things like that. Okay, so here's a function where we're calling h. Inside that function, we're doing 2 is storing into a, and then we're doing x plus a, right? And then so if we say y is h of 1, y is going to take on the value what? 3, right? Okay, and so what's going on there is so h exists in the global environment. This is the enclosing environment of the function. H is also the binding environment. So when we execute h, okay, it suddenly creates its own little magic, not magic, but its own temporary execution environment, right? When we called h, we gave it the argument x is 1, right? Okay, so that's going to put x is 1 inside this execution environment. When it runs through the code, it goes to the next line of code, and it goes, inside here we're going to do a is assign the value of 2. That happens inside the execution environment. Nothing in the global environment is affected. Okay, and then finally it it goes x plus a, so it goes 1 plus 2, and so the function returns a value, and it's stored into the value y. Okay, so y gets created in the global environment, and it has the value 3, and this execution environment, poof, it's gone. Anything that happened in here, there is no recollection of it. It happened, it's done, and we don't remember anything. We only see the effect of the function here. Okay, and then and so yeah, if you're calling I guess the important thing is that this is the global environment. Here would be the enclosing environment. So if you're employing lexical scoping in that it's searching for values higher up in the tree, it's going to start its search here in the global environment. Right? Okay. When you call a function, it creates an execution environment, and the execution environment itself has two parent environments, right? The enclosing environment and the calling environment, right? If you created a function in the global environment and call the function while you're in the global environment, then these are the same. The calling and the enclosing environment, those are going to be the same, all right? But in some cases, you might call a function from inside another function, all right? And in this case, the enclosing environment will be the environment where the function is created, okay? But the calling environment is the environment where it was called. So in that case, the calling environment is the function that is calling the other function, right? All right, and so the scoping rules in R will use the enclosing environment, okay? And so when if you're calling function g from inside function f, and g is performing some kind of lexical scoping and it's searching for other things, it's going to go to the enclosing environment, right? And it's going to start its search there. So if g is created in the global environment, it's going to start its search inside the global environment because that's the enclosing environment. There is something called dynamic scoping where you can tell g, hey, I called you from inside f, and so when you do your scoping, don't start your scoping the normal way. Start your scoping from inside the function where I called it, okay? That's dynamic scoping. And I would say that that's used in like kind of this non-standard evaluation, which we're not really going to get to in our class, okay? You can, the later chapters in Hadley's book, non-standard evaluation, if you want to sit down for, you know, a few hours and figure this out and learn about it, it might be worth your time. It might also just be like, man, this is more than I need to know. So, but you know, if you want to be a guru, then you can do stuff like that. Okay, but so that's dynamic scoping, where you can take advantage of the fact of you know, maybe there's variables from inside the calling environment that you want this thing to look at. And that'll be dynamic scoping. Okay, that's something else. Again, most of the time, you know, if you're calling functions from inside the global environment, then the calling in the enclosing environment will be the same. But if you're calling a function from within a function, then you have different calling and enclosing functions. The general rules is that the scoping uses the enclosing function. If you want to use the calling function, then that's dynamic scoping. All right, is that okay? All right, now we're going to enter on this topic of debugging. All right, so we'll talk about how to fix unanticipated problems. Okay, that's just the general idea of debugging. All right, and then how we can do some error handling. Okay. So communicating problems, we have conditions, all right? We've got errors, we have warnings, and we have messages. So like during your function, if something happens, you can have it, stop, okay? And that's gonna just stop the code and kick back an error, right? And then sometimes you weren't expecting it, and then it just stops, right? It just spits out an error, okay? Warnings are used for something, maybe something happened and we weren't expecting it. That's going to be a warning, but it can still run, all right? And then you can also just use messages, which are not necessarily warnings, okay? They're just like okay, and you can suppress messages, all right? So conditions are displayed prominently, in that generally when you're running R and you're going to get some kind of warning or some kind of error or something like that, or a message, they appear in red, right? So when you do like print or cat, in the output they just show up as plain black text, right? When something goes wrong, it'll generally show up in a different color, red, or whatever whatever theme you've applied to your thing. It makes these show up differently, okay? So versus print and cat, those are going to just appear regularly, okay? And those things are not conditions, so you can't use condition handling tools, right? Okay, so as far as debugging goes, this is kind of like common sense tips, but it's like these are the ways you try to fix your bugs, all right? So first you got to figure out that you have a bug, and then you want to make it repeatable. So if you're getting some kind of error or something is happening that you're not expecting, you want to be able to figure out exactly what set of conditions are causing this thing to go, right? Like if you run the code once and it works, and then you run it again and it doesn't work, and then you run it again and it works again, then that's something very tricky, because you don't know exactly what's causing it. But if you can figure out, oh, under this exact condition, it's breaking on me, okay? Then you can start to figure out what's going on, right? And then you got to hunt it down, and then you fix it, and then do some testing to just kind of make sure that it has worked, okay? So here's this quote that just says, fixing a buggy program is a process of confirming one by one the many things that you believe to be true about the code are actually are true, all right? And then when you find out that one of your beliefs or assumptions is not correct, you have found a clue to the nature of the bug, right? And so it often helps to break your code up into manageable chunks, and that way you can just do one chunk at a time and make sure it's doing exactly that you're expecting it to do, okay? So in tic-tac-toe, I've kind of broken it down for you. I said, like, program at least these 4 or 5 functions, and you can make sure that each function, you can kind of test them separately to make sure that they are working the way you want them to work. Okay. And in some cases, it might be worth writing 2 versions of a function. One where the performance is poor, but 100% that it works correctly. All right, and then another one that might be working better or is more efficient, but it's harder to be sure about. Okay, and then you can kind of test both of those to make sure that they are producing the same outputs in all scenarios. Okay, and then and when errors do occur for certain inputs, they are often the edge cases. All right, situations which are on the boundary between legal and illegal inputs. Okay, so when you get error, it might be because you're giving it a vector of length 0, or very large values or very small values, or something where it's kind of like maybe this is allowed or this isn't allowed, right? Yeah, obviously you can't give the log function negative values or things like that. So it's good to try to figure out what your edge cases are and figure things out. And often it's the edge cases that are difficult, right? So I remember watching this video. Do you guys know, like, Isaac Asimov's laws of robotics, Or it's like rule 0, it's like don't destroy humanity, and rule 2 is like don't bring any harm to people, and rule, I don't know, what are they? Rule 1 is like don't bring harm to people, rule 2 is don't bring harm to yourself, and rule 3 is like obey the owner or something like that, right? And it's like, oh, that makes sense, but then it's really the edge cases that are hard to decide, right? Like, what does it mean to harm a person, and who counts as a person, right? Like, and this is something that we have policy debates about, right? Like, who exactly is a person? Is someone who's on life support and has no brain activity, is that still a person? And in that case, is it okay to kill this person without legal ramifications? Because if you kill anybody else who has brain activity, then you're in legal trouble. But then I don't know, right? So anyway, the edge cases are often, well, in computers you probably don't have to solve ethics, but well, I mean, maybe you do, right? Like, should the car crash into the wall to kill the driver, or crash into, right? That's the ethical problem of self-driving cars these days, right? Like, and who knows, right? And who's going to buy a car that says, oh, if we had to choose between the crowd and you, the car's going to kill you? So, but that was the most ethical thing to do. All right, I don't know. All right. All right. All right. Oh, automated testing. Most of you are testing your code as you write it, right? You usually write a little thing, and then you just say like, oh, is it working the way I want it to work? That's almost like a natural thing, right? Nobody writes 100 lines of code or 1,000 lines of code and goes, okay, well, I hope it works now. You usually write like 2 lines, and then you get them working. You're like, yes, I'm a genius, because I got these 2 lines to work. So anyway, oftentimes when you're doing this, so that's like the informal approach. It's good at least to write down on a separate piece of paper or in a separate file the test cases that you're using, right? So you can keep track of all of these things that you tested, and it's giving you the correct output that you want. And because sometimes later on, you might change another piece of code somewhere else, and it happens to break the whole thing down. And then you have to go back, and you have to say like, okay, did it work for this case? Did it work for this case? And you're like trying to remember all of these funny cases where it's working or it's not working and things like that. Okay, so at least if you keep track on a separate file all of these cases where it should work, and if you have like the code already written, like make sure it works for this case and this case and this case, then it's really easy to test all of those cases. And Hadley has written packages for automated testing. It might be a little overkill at this point, but with automated tests, it basically creates a system for you to do all of those test cases where you say like, when you run this, it should come out to be this, and you give these things like, run through all of these things, and then if when it runs this and it's not equal to this thing I expected, then tell me that it broke here on this situation. Okay, but it's much better than just trying to keep track of all of these things in your head. At least just on a piece of paper, like, oh, if I put the X here and the X here, is the computer gonna block this spot? It should, right? All right, so anyway, make the bug repeatable. All right, and so it should always work. Anytime you're using a randomizer inside your thing, like generate random numbers, this is where the repeatability thing gets a little bit more complicated, because it's like under certain things it works fine, and then like for whatever reason the random thing generated something, and now it's broken, right? So if you set the seed, it should behave exactly the same every single time. But then when you turn that off and you run it over and over again, you might be able to keep track of things. So and so if you're using, so in this early stage where the code is kind of breaking on you, it might make sense to, when you have it call sample or have it call, you know, random this, store the output of that random thing so that during your traceback or the browser mode you can see exactly what random value it generated. And then you're like, oh, it generated a negative number and that was bad or something. Okay. All right, and then all of this. So identifying the cause of the bug, we'll look at traceback in the browser, and then you fix it, and then you do your tests again to make sure it's working in all of the scenarios. Okay, so we have a few tools for you. They're already implemented in RStudio, and well, they're also in just plain old vanilla R also, but then RStudio makes certain things easier. You've got the traceback, and then you also have browser, and you can do kind of set breakpoints. Okay, so let me find this and this. Okay, so here I'm going to create a function where A is calling G. F calls G, G calls H calls I. These are like the dumbest functions ever, right? Okay, and then I is trying to add the letter A to D. Okay, so of course this is going to result in an error, right? But then, okay, and then but you can imagine a scenario where you have all of these, like one function, somewhere in that function it's calling another function and something like that, right? Okay, so then we say, okay, now I want to run f of 10, right? And then it says, okay, it says error, you're trying to add A to D, okay? And you're like, well, I don't remember ever seeing a D, right? F is a function of A. So what's going on, okay? So you can do show traceback, right? And then you read from the bottom to the top, okay? So you say, okay, when I ran f of 10, okay, the thing that is being executed is it's running code g of A, okay? And then g of A is going to call h of B, all right? And then when you call that, it's running I of C, and then in function I, that's where it's running into this thing, okay? So it kind of shows you the path and the code that it took to get to this thing. And then you can say, oh, okay, you're right. F is a function of A, and nowhere is it talking about D. But now that I know that I called I a thing, this gives you a clue, and you go like, okay, well, let's see what I is doing, right? And we go, oh, there's my problem. I is calling, it's trying to add A to D, okay? And so we can see like the 10 has been passed to this D thing, and then now we're trying to add A to it. And then we can say, okay, well, this is where I need to fix it. Maybe I want to change this to 2. Okay, and then you fix your code there, and then now it runs. Okay, so yeah.
How do you find out there's something wrong with I function I?
How do we know? Because the last thing in the traceback was a call to I. Okay, and so this is where the error occurred. The error occurred after this line of code was executed. Okay, so we can see, right, because the problem is that you ran function f, okay, and when you run function f, the error you're getting is A plus D, and you're like, that's not part of function f, right? You're looking at function f, and you're like, and there's you imagine the code for the function is much more complicated, and you're just like, I don't see A plus D anywhere in this function, right? And then so traceback tells you, okay, you started here, and then basically the series of code that brought you to this point, the last thing that was run before the error was function I. And so this will give you an indicator that the error is somewhere in this function I, and somewhere in function I, you're trying to do A plus D. Okay? Okay, so, I mean, so these were just overly simplified examples, but you can imagine in each of these functions, you know, it's totally normal to be calling functions inside other functions, but then that you lose some clarity in, like, because you said, well, I just ran function f, but I don't remember ever seeing any of this other stuff. Okay, so that's traceback. You can just so when you get an error, you can often just click show traceback, and it does that. You can also let me just put this back. Okay, and then I run this. You can do this. You can also type in traceback. This is before RStudio. This is how people had to do it, and then it says this is you get the same thing. Okay, but now we can save you a few keystrokes by doing that. Okay, but it's the exact same thing, right? All right. Okay, so we have traceback. Okay, and then we have the browser, right? And so the browser will put you in an interactive state inside the function, and you can interact with any object defined there. So, so again, when you run a function, it creates its own little execution environment, right? And generally, the function runs, the execution, it does all the stuff inside the execution environment, and then at the end of the function, that execution environment, poof, disappears. Okay? Sometimes you're like, the function isn't giving back what I want it to give, and you want to know what's happening inside that execution environment, right? Because you're creating things and you're reassigning values inside that execution environment. Browser allows you to enter that execution environment, and then you say, hold up, code, stop here, and I want to see what the values are at this point in time in the execution environment at this line of code. And then you can say, okay, X has the value I expected, Y has the value I expected. Let's run the next line of code. After this next line of code, X changed the way I expected. However, Y changed in a way I didn't expect. Okay, so now I know that whatever line of code I just ran is doing something in a way that I was not expecting. Okay, and so the browser allows you to enter kind of that execution environment, see exactly the values that are being thrown around, and then that might give you insight into where your bug is. Okay, so let's so here are you guys let's see, okay, are you guys familiar with bubble sort? Okay. All right, so bubble sort is a way to sort numbers. Okay, and the way it starts is, you got this thing, and what it's doing is it's looking at two numbers at a time. This is from Wikipedia. I didn't come up with this animation here. Okay, it's looking at two numbers at a time. If the number on the left is, if the number on the left is bigger than the number on the right, it swaps these two. Okay, and it goes through, and it keeps going. So 7 and 8. So 8 is bigger than 2, so it's going to swap 8 and 2. Okay, and then it goes through here, and it's going to swap 8 and 4. Okay, and now that it has done this, we know that 8 is in the proper position, right? Because it's starting over here, and it just says, look at these two numbers. If one is bigger than the other, swap it. Okay, until you get to the end where now this is the biggest thing. Okay, and it's just going to keep doing that, and then so we can keep staring at this, and it's gonna do this. It's gonna swap the 7 and the 2, and it's gonna swap the 7 and the 4, and then now we know the 7 is in its proper location. Okay, so anyway, let's so I have bubble sort coded up here, and it is coded correctly as far as I know. But maybe you are curious how this thing is working, right? So here I have x is just this vector of 6 values, right? And we want to run bubble sort on this. Okay, so I can run this thing, and if I run bubble sort, indeed, it's sorted 1 through 6. Okay, so now maybe we want to see what's exactly happening here. Okay, so I'm gonna set a breakpoint. You can just set a breakpoint here by clicking in the margin. It says breakpoints will be activated when the file is sourced. So I'll go ahead and oh, I have to let me tell it not to run that code. Okay, so we'll okay, so I activated a breakpoint here. Okay, and so now you can see the environment that I'm in is this execution environment for bubble sort. Okay, and the values that I have are I, and j. Okay, so j is length of x to 2. So it's going to go from 6, 5, 4, 3, 2. Okay, so currently it's at 6. I starts at 1 and goes up to 5. Okay, and then right now x is this integer vector of 2, 6, 3, 4, 1, 5. Okay, and I can just see kind of like what is x, and it's going to run this thing, and so we can see, you know, x sub I is 2, and we're going to see is x sub I versus x plus 1. We can see what it's going to say is 2 greater than 6. That's not going to be true. So we can just click continue, and so we know that this thing is going to be evaluated false, right? We can say is this going to be true? You know, x sub I, is that greater than x I plus 1? That's going to be false, so it's going to skip all of this thing. It's going to go to the next pair. All right. So if I click continue, all right. So it so we go there, all right, and then so now the only thing that has changed, we can see I has incremented to 2. Okay, and then so we can see, all right, what is x of I? And we say, oh, okay, x of I is 6, and x of I plus 1 is now 3. Okay, and so when I click continue, we know this thing is going to be true. All right, and so it runs through into the next thing, and we can see that you know, it has executed the code that goes in there. All right, and so the browser allows you to kind of take steps into this thing, and or I'm sorry, I should have clicked next. Sorry, just for that next line of code. Okay. All right, we'll stop there.